So now I'm making a different case, extending this in another direction. And again, I think this visualization might be helpful. So now if I look at, for Amdahl's law, so let me just go in here.
Yeah, put that on the top. So I sort of see this classic measures, these are constantly being referred back to.
Right,
So I'll
exactly.
keep them as a base. Okay.
And now Amdahl's law, it's about speed up again, right? So this is all about speed up so far. Load
Right.
balancing helps you get better speed up.
Right.
If all you do is change the ratio, right,
Right.
and make it as equal as possible between the machines. Now Amdahl's law is about, instead of being able to run anything of that job in parallel, there's now this inherent sequentiality, right? So you have your work to be done. Now it consists of two phases. Phase 1, phase 2, and there's this dependency that phase 1 has to happen before phase 2. So you cannot do them both at the same time, right? Because maybe there's some
Data that's dependent on.
intermediate result, right? That has to be fed from phase 1 to phase 2. So phase 2 has to wait until phase 1 is done. And I can give some concrete examples for that, but visually it would just be like that. And now we know that overall the work is still one, right? It's the same as before, but it has now this extra structure of these two phases.
Okay.
Now we also know that phase 1 is perfectly parallelizable.
Is that a word?
I don't know, I'm just using it. And phase 2 is inherently sequential. So it cannot be run on multiple machines, right? So it's something that just has to be on one processor. So now if I think about what kind of speed up can I achieve, right? So visually what I would like to show is something like this. I have my initial picture like that. Initial picture is phase 1. And phase 2. And now this is on one machine. Now if I use two machines, instead of getting this here where I cut the whole thing into two pieces, I can only cut phase 1.
Phase 1
right?
into 2, right.
So what I would like to do is something like this, right, where I have now phase 1 gets cut into two pieces, and now if I look at my machines, machine 1, machine 2, now one of these goes to this machine, the other one goes to the other machine. They're both perfectly balanced, right, same size, so this is P1 halves, P1 halves. But then we have to still run phase 2, right? So that one, it doesn't really matter on which machine it runs. It runs on one of the two, so we can either add it just to one of the two, wherever it fits better, or in the middle between them, but it has to be in the end running on one of the two. So the correct way would be to put this either here or there. But in some way, since it doesn't matter, we could also just add it in the middle. And then if you look at the overall runtime,
And you can't split phase 2 into 2 different machines?
right, exactly. That's this one that's inherently sequential, right?
Oh,
There's
no.
no way to cut it into multiple pieces.
Okay.
And so now if I look at the running time, or whatever I called it before, time to process, so we have to use some consistent notation, right, execution time, whatever I want. This one take time 1 on one machine, right?
Mm-hmm.
Now how much time does this take? We have to introduce a new variable, right? Let's say we call this one T1, right, in terms of the time, running time. What time to compute T1, and since the whole thing takes 1 over all together, right, then this one is 1 minus t1, right? So now if I look at how much time does it take here, this first phase takes t1 over 2. The second phase still takes 1 minus t1. So the total running time is t1 over 2 plus 1 minus t1. Right.
Okay.
And then I can simplify that, right?
So what do you want them to see? This equation at the...
Right, so I want them to see this equation also. And then you can see how it generalizes, right? Instead of 2 machines, if I use n machines, how does this change, right? So, well, this one is still the same. This one turns into t1 over n, right? So in general I get t1 over n plus 1 minus t1.
What is n machines? Is that more than 1 machine?
Yeah, whatever your n is,
Oh,
right?
the
2,
whatever.
300,
Okay.
1,000. Like the same here, right?
Yep, for 3, right.
I just went up to 3, but you know, I can go to any number I want.
Okay.
So I want to say in general, if I have any number n,
Right.
let's say greater or equal to 2, right, I get this. It's even true for 1. But,
Okay.
so what do I get as my formula, right? I can simplify that again. This is 1 minus n minus 1 over n t1, right? Is it correct? Minus 1 t1. Anyway, we can double check that later. But, you know, so then I want to derive this general formula. And this is the best possible speed up that I can achieve.
That formula is Amdahl's law for the best possible speed up, or is,
Right.
yeah,
So it basically says if you have these 2 phases,
right.
one of them cannot be parallelized. The other one, even if it's perfectly parallelizable, right? It doesn't matter what you're doing. You perfectly balance the load for this first phase. The second one is always there as this big chunk, right? And it doesn't go away. And so if you now think about n, even if you use an infinite number of machines, this one goes closer and closer to 0. This one is still there, right? So if you let n go to infinity, this one approaches 1 minus t1.
Okay.
And then I put in these concrete examples where I say, okay, let's look at some numbers like t1 equals 0.9, which means 90% of the job is perfectly parallelizable, and only 10% is this sequential phase.
So you're in class asking them, let's plug in some numbers.
Right. And then I go on the board and say, let's just put, you know, let's assume we have 90% of the job is easy to parallelize, right?
Okay.
And only 10% cannot be. And now let's say we're using 2 machines. We put the numbers in and we say, this is the best possible speed up I can hope for, 1.8, right? And then I put bigger numbers where I leave this 90% the same and I increase n. And it kind of, this is I think the really interesting case that at some point, the more machines you add, you get less and less benefit per machine, right? Even with 100 machines, your speed up is only 9.